Okay, so let's look at a couple more examples of computing volumes of solids of revolution, where your axis of rotation is some other line other than the x-axis. So consider this example. You're given the region between the square root function and y equals x to the fourth power. And you're rotating this not around the x, but around the y axis. So what does that look like? Well, let's draw the graphs first. We know that they'll intersect at the point 1, 1. And this is what the square root function looks like. Let me make this a bit nicer. Nope. So hard to draw on this using a stylus. Okay, so this is the point 1, 1. This is square root of x, this is x to the fourth power. But now what we're doing is we're not rotating around x, we're rotating around y. And what that's going to look like is, so there's going to be a mirror image here of both curves. All right, and then rotating around like this. And that's what it looks like, the solid you're getting. Now, again, remember that, well, what I've been saying since 2 videos ago. In order to compute volume, you just need to know what the area function is, right? Whatever this area is that you're accumulating. But the issue here is, well, we're not slicing it perpendicular to the x-axis anymore. If we were to do that, right, then you wouldn't be getting circles when you slice it like this. When we slice it perpendicular to the y-axis, then we're going to get circles. In fact, we're going to get washers as well, right? But now we're getting one washer for each y coordinate. And this is pretty much the only difference between rotating around the x-axis or the y-axis, is that now you're taking horizontal slices of your solid. And well, I'm going to use the same formula here, but I'm going to write a of y dy, just to emphasize that now we're getting a slice for each y. And the question is, again, the same question. Can you give me a general formula for whatever the area of this washer is, right, for any y coordinate that I pick between y equals 0 and this is y equals 1, right? Because I'm getting a slice for all of these y values. So how do we get this area function? Well, now if you look at your washer from the top, right, this is what it's going to look like. Well, a washer, right? So a circle inside another circle. And now you really just need to determine what this outer radius is and what this inner radius is. Right? Again, for washers, it's going to be exactly the same as for the x-axis rotation, just that it's going to be dependent on y instead. And the area function can be written in this manner, sort of independent of whichever variable you're looking at, right? It's just, you can think of it this way. I need to know what the outer radius is of that bigger circle, the inner radius of that smaller circle. And so in this case, at that specific y coordinate, how do I get this inner radius and this outer radius all the way to the right? Well, I have the functions to help me do that, right? So let's draw them separately here. The curve that defines the inner radius here is the square root function, y equals square root of x, right? But we're not concerned with this value, right? That vertical segment. Instead, what we want is this horizontal segment for a given value of y. So at y coordinate y, what is this length equal to? Well, note that we can write this as y squared equals x, right? And in a sense, what we've done here is to view this function as a function of y, where y is your independent variable, right? You plug in a y, and you get a corresponding value for x. Right? So instead of moving to the right and upwards, now you're moving upwards and then to the right. And so this is nice, because now this tells me this point can be described as y squared comma y. And so for each value of y from 0 to 1, this inner radius is just y squared. Right? And by the same reasoning, looking at my alter function here, y equals x to the 4th power, right? Again, for this larger radius going to this curve outside, you can do the same thing at a specific y coordinate. You're computing what the corresponding x coordinate is. Well, okay, y equals x to the 4th power. We're in the first quadrant. So this is the positive 4th root of y. Therefore, this point is going to be the point y to the 1/4 power, comma, y. And this y raised to 1/4 gives us exactly what this outer radius is. And you just plug them in. And this is your area function. Right? And again, I'm not going to compute this integral anymore. But you have your area function. You just need to plug that into this integral and integrate from 0 to 1. Now let's look at an example that we did in the previous video, which is this region between sine x and cosine x. But instead, rotate that around the y-axis. And what's going to happen here is, well, maybe you can try thinking about this for yourself first. If you want to pause the video now, just try to imagine what will happen when you do this rotation. Okay, so you probably saw that you don't get washers here, right? In fact, my graph here is not really in the best location. Let me draw it again here. Right, so if that's my solid, if that's my plane region, and this is the y-axis, and I'm rotating around the y-axis, what's going to happen is I'm going to get a region here on the other side of the y-axis. Right, so I'm just kind of using this to guide my drawing here, where my cross sections perpendicular to the y-axis are just circles. But wait, what's happening, right? I have two curves here. Why don't I get washers? Well, that's because one curve is not inside the other. What's happening here is your area function, a of y, is actually going to be a piecewise defined function, because whatever the radius of this circle is depends on which curve you're using, right? Remember, this point here is the point pi over 4, comma 1. no, not 1. Why did I say 1? Pi over 4, comma, 1 over square root of 2. So this means that from y coordinate 0 to 1 over root 2, which is this line, my radius is going to be given by, well, this is the sine function, right? So this is the point. Remember, we're viewing these functions as functions of y now. So this is going to be the sine inverse function. From 1 over square root of 2 to 1, for every cross section that I have up here, this radius is now going to be given by the inverse cosine. And so what's going to happen is when you have to integrate, the volume is, well, it's still 0 to 1 of your area function dy, but your area function is a piecewise function, right? So what that means is you have to split the integral up into 2 separate integrals. And if you don't know how to compute this, it's okay, right? But we've set up the integral for the volume of the solid. And now, one last example here that I want to talk about in this video is a slightly weirder example where we're rotating about not the x-axis nor the y-axis, but the line x equals -1. So it's this line over here. And the region under consideration is this region between y equals ln x, y equals negative ln x, right? So remember the natural logarithm looks like this, has a vertical asymptote at 0, passes through the point 1, 0. So the negative of ln x is going to be the same function, just reflected across the x-axis, right? That's what the negative sign does to a function. It flips it across the x-axis. So that's why we get the negative here, and this is the original ln x function, right? So we're looking at this in between x equals e raised to -1 and x equals 1. And e to the -1 means, well, if that's the x coordinate, then the y coordinate is just either -1 or 1. So this is the region that we have. And we're rotating it here now. Not across the x-axis, but across or around the line x equals -1. Oh, sorry. Okay, so this is a typo here. This should be y equals -1, right? Clearly, this is y equals -1. It's a horizontal line. So that's what I meant to ask. So we're rotating about this horizontal line, y equals -1. So cross sections, when you take slices of the solid that you get, that's perpendicular to this axis of rotation, well, they're going to be washers, right? Because you have a curve that's outside and a curve that's inside. And again, if you look at the solid from this perspective, right? If you look at the washer from that perspective, again, you're going to see two circles, concentric. And again, the question is, again, exactly the same, right? The volume is going to be the integral of the cross-sectional area from e to the -1 to 1, right? Your x coordinate on the left and on the right. But what does the radius look like for the outer radius and the inner radius, right? So that's the question now. So let's look at the inner radius first. Given any x coordinate here where you're taking your slice, what is this length going to be equal to? So let's draw that separately here. This is the x-axis. This is y equals -1. And this is y equals ln x. What we're asking is the question, at this x coordinate, what is this length here? Right, so that's here. Well, what I do know is the coordinate of this point, right? At this x coordinate, that point is going to be ln x for the y coordinate. But what does ln x give me? Well, ln x gives me this distance, right? Ln x is going to be negative there, in fact, right? Because it's below the x-axis. What I really want is this other portion here. So how do I get that? Well, how do you get the distance between two numbers? That's the point x comma -1. This is the point x comma ln x. Well, you just have to subtract the y coordinates, right, to get that length. And so that tells me that this inner radius here is going to be equal to ln x plus 1, right? Because it's ln x minus -1 to get this length over here. And you can think about doing the same thing for the outer radius. At the same x coordinate x here, this outer radius is going to be equal to, well, this has y coordinate -ln x. This has y coordinate -1, right? That's the center of your circle. So the radius is going to be the difference, -ln x minus -1, which is -ln x plus 1. Right? And so that gives me whatever this radius is. And so now I have my area function, right? For washers, it's just pi times the outer radius squared minus pi times the inner radius squared. And again, don't worry too much if you can't quite evaluate this integral yet. But this is going to be equal to the volume of that solid.